Hello everyone, myself Dr. Priya Vashisht, working as an assistant professor in School of Chemistry and Biochemistry, Thapar Institute of Engineering and Technology, Patiala. I welcome you all to the series lecture of phase rule, and in that series this is the third video, and by the end of this session the participants would be able to well understand what do we mean by reduced phase rule or condensed phase rule, what do we mean by two component system, and how do we apply this two component system to simple eutectic systems. The sequential order of the video will be the reduced or condensed phase rule, that why do we require reduced or condensed phase rule, how did it originate, two component system, and in the category of two component system we'll be taking up simple eutectic systems as per the syllabus. Now before we come to the two component systems, it is very important to understand what do we mean by reduced phase rule and why do we actually require this. Why cannot we apply normal phase rule as we discussed it in the one component system? If we see for a two component system, C is equal to 2. Therefore, if we apply phase rule and we calculate the degrees of freedom, it comes out to be F is equal to 4 minus P, putting the value of C is equal to 2. And for evaluation of maximum number of degrees of freedom, the phases should be minimum. Like if I put P is equal to 1, I get maximum degrees of freedom, that is F is equal to 3. What does it mean? That I require three variables. Three variables will be temperature, pressure and composition, or you can say concentration, to explain the system completely. That is, if I want to explain the system, two component system applying normal phase rule, I require three variables, that is temperature, pressure and composition. It simply means that if I require three variables, it has to be done via a three-dimensional diagram that is very difficult to represent on paper. But we actually need to represent it on a two-dimensional point of view as we did it for the one component system. That is, to construct a single phase diagram for a two component system, any two of the three variables should be chosen for the graphic representation and one has to be kept constant. Only then that is possible. So the what possible cases may arise are pressure temperature diagram, that is PT diagram, when composition is constant, temperature composition diagram when pressure is constant, pressure composition diagram when temperature is constant. Now out of all this, experiments are generally conducted at room temperature. Hence in most cases pressure is kept constant, that is 1 atmosphere, and the phase diagrams are constructed using the variables temperature and concentration, or we can say temperature and composition. Moreover, in the solid liquid equilibrium, the gas phase is generally absent. When you consider equilibrium of a solid liquid, that is in a solid liquid equilibrium, the gas phase is absent and consequently the effect of pressure is negligible. This system, such solid liquid equilibrium with the gas phase absent, is termed as condensed system. So before we understand what is a condensed phase rule, we need to understand what is a condensed system, what kind of systems will be taking up in the two component systems. We'll be considering only solid liquid equilibrium and hence we name them as condensed systems. Keeping the pressure constant, as I told you, we'll be keeping pressure constant. If I keep the pressure constant, that is, I have held 1 degree of freedom, I have reduced 1 degree of freedom by 1, and for such a system, now the normal phase rule, that is F is equal to 4 minus P, will not apply, rather it will be 3 minus P. So we represent the reduced phase rule by F prime is equal to 3 minus P. That is, we have reduced 1 degree of freedom by keeping the pressure constant. This is known as reduced or condensed phase rule, and this is applicable to solid, liquid, two component systems, and we will apply this in the upcoming slides. The solid liquid equilibria are hence represented on temperature composition diagrams. As in the one component system, we did temperature pressure diagrams. Here we'll be considering temperature composition diagrams. Now, in this category of two component systems, as per our syllabus, we'll be taking up simple eutectic systems. In the category of two component systems, there are various systems possible, but for our syllabus point of view, we will be taking up simple eutectic systems. Now, before I proceed further with what are these systems, it is very important to understand the meaning of the word eutectic. The term eutectic means easy to melt. The term eutectic means easy to melt. What are the systems? What are the substances that form eutectic systems? How can we say that these two substances will form a eutectic system? Or you can say, what is a eutectic system? A binary system having two substances, binary means two, having two substances which are completely miscible in all proportions. Completely miscible in all proportions means they form one phase. They are completely miscible in all proportions in the liquid state but immiscible in the solid state. They are known as eutectic. Such systems are known as eutectic system. For example, a mixture of lead silver comprises such a system, and this will be discussed in the upcoming video as an application of this system. The very important characteristic of some eutectic systems is that they do not react chemically and they have tendency to lower each other's freezing point. That is, if I have two systems and they certainly have a melting point, when they are mixed together, they have a tendency to lower each other's freezing point, and I'll be taking up how this takes place in the upcoming slides. Now, what is eutectic point? In this slide, I am taking up very important definitions that are very important from your examination point of view also. That is, whenever you get a question of simple eutectic system, you're always required to define eutectic system, eutectic point and temperature mixture very precisely. So, though I am taking up these definitions right now in the beginning, but as I proceed in the video and as I explain you the eutectic system in detail, you will be able to define these points and definitions on your own without just cramming them. Eutectic point, when two or more solid substances capable of forming solid solutions with each other have the property of lowering each other's freezing point. That is, when two solid substances, they are miscible in each other and form solid solutions, they have property to lower each other's freezing point. And for a certain composition, at a certain composition, there is a minimum melting point that is attainable. That below that point, the melting point cannot be lowered. That point is known as eutectic point. This will see practically as we proceed. What is eutectic mixture? The composition corresponding to a point, eutectic point, is known as eutectic mixture. That is, it is a solid solution of two or more substances having the lowest freezing point of all possible mixtures of the components. That point, that temperature where the minimum melting point was there, that corresponding composition is known as eutectic mixture. These will be more clear to you as we proceed further. Now, very important, simple eutectic systems, the characteristic is majorly that eutectic mixture has a definite composition and a sharp melting point. That is, if you are combining two components A and B, there will be a definite ratio of A and B in what they combine that corresponds to a sharp melting point. That is, it melts to a liquid of the same composition. As they were present in the solid phase, they will be present in the same composition in the liquid phase. They will melt with the same composition. That is, it resembles a compound, but it is not a compound, as the components are not present in stoichiometric proportions. So it is very important to understand that they have definite composition, but they are not compounds. Now, this is the phase diagram of a simple eutectic mixture, and as I told in the one component system, that it was very important to visualize the one water system. You don't need to design that system, but in this case, from the eutectic point of view, when I discuss this phase diagram with you in detail, we'll be taking up in detail, even if you are giving, this is the diagram corresponding to general eutectic system considering any two components A and B. But if in examination you have been given any two arbitrary components A or B, and they have been assigned certain melting points, and there are certain conditions assigned to you, that this is the composition when they form a eutectic mixture, this so and so is their melting point, you should be able to construct this phase diagram, and that is very simple for you. By the end of this video, I'm sure you'll be able to do that. So apart from visualizing it, we need to understand how these graphs are being traced and what is the significance of each and every point and curve. So before I proceed further, let's understand the x-axis. Y-axis represents the temperature and x-axis represents the composition. Here this is 100% A, that is pure A is present at this point, and here this is 100% B, that is pure B is present at this point, and this composition is expressed in terms of percentage. No doubt it can be expressed in terms of mole fraction also. The difference will be there, that instead of 100 we'll be taking 1 in that case. Now on this axis, as you're already familiar with the composition diagrams, percentage of A, percentage of B, if the point is lying closer to A, as is lying this X point, obviously it will have more of A and less of B. If there is a point at this point, if you name it as C, if you name it as L or C or whatever, but my point is, if it lies well near to point B, it will have more of B and less of A. So this is how we see the composition point, and this is the temperature axis. Now we'll proceed further to understand that what actually happens when we add A to B or B to A to form eutectic mixtures. Now let's take this one by one. I'll be taking up, as I've written, ABD case. This ABD case is the actual case, how you will be able to understand how this is being done. In this diagram, the points A and B represent the melting points of components A and B. That is, A is the melting point of pure A and B, capital B, is the melting point of pure B. It signifies that below this point A, the component A exists in the solid state, while above its melting point or freezing point, it exists in the liquid state. Similarly for B, below this point it exists in the solid state, while above it exists in the liquid state. So A and B are melting points of pure A and pure B. Now for example, on this composition axis, we have considered a particular composition X, or you can imagine that in a beaker you imagine an arbitrary composition corresponding to X. Let's assume that it has to, and you have taken it in a beaker and you have started heating it, and you have heated both the components well above their melting points, and they both have melted, and now in a beaker you have a liquid solution that has both components A and B, and say it has reached point A. Now, when it has completely melted and you have just liquid state, now let's assume that this liquid mixture of composition A is cooled at a constant pressure. Obviously, we have assumed that the pressure is kept constant and we are plotting TC diagram. So, liquid mixture of composition A is cooled at constant pressure. Now, if we go on cooling it, what are the observations? The temperature will fall without any change in composition up to the point B on the freezing point curve AC. That the temperature will fall without, there will be no change in composition, because this line, dotted line AX, is representing the composition. Obviously the composition is not changing when the dotted line AB is traced. So temperature will fall without any change in composition up to point B on the freezing point curve. Now, what do we actually expect when you start cooling the mixture? That when you start cooling, when this reaches, this point is well above, this point A is well above the melting point of both A and B, only then it was in the pure liquid state when we heated. But now when we start cooling it, we expect that as we reached the melting point of component B, it should start freezing out. But actually it does not happen. So why it actually does not happen? Because now here comes the concept of, if you remember in your lower classes, you have done Raoult's law, colligative properties. According to that, if some impurity is added to a pure component, then its freezing point is lowered. For example, if you have pure water, freezing point is 0 degree centigrade. But if salt, urea or something else is added to it, its freezing point will be lowered. Now, since this is not pure A and this is not pure B but mixture, it will not melt corresponding to the point B. Now, as you go on cooling, at point B, corresponding to temperature T1, that is well lower than the melting point of pure A, solid A will start separating out, because the melting point of A was lower than that of B. Now when you go on cooling, at a temperature T1 that is below A, because A will also not start separating out at its pure melting point, because obviously its freezing point will be, or melting point will be, lowered. They have tendency to lower each other's melting point. So at point B, corresponding to composition this, at temperature T1, solid A will separate out. And now what do you have? Now at point B, when solid A has started separating out, you have liquid solution of what? Having both components A and B and solid A. That means you have now two phases. One phase is being composed by solid A and the other phase is being composed by miscible liquid that has both A and B. If you calculate degree of freedom for that, it comes out to be monovariant. Now temperature will fall only with change in composition of the liquid phase. Now temperature will only fall if there is change in the composition of liquid phase. What does this actually mean? That if you go on cooling the solution further, once the component A has started separating out from the point B, and you further go on cooling it. If you further go on cooling it, more and more A will be separated out from the mixture, and obviously the composition of the liquid phase will change now. For example, you say arbitrarily, you imagine that out of 80 gram of mixture, 20 gram of A was separated and 60 was, what do you say, the composition of A and B. But now more and more A is separating out, and hence the composition of the liquid phase will go on changing. If I say more and more solid A is being separated out, it means your solution is becoming richer in B. What is the component which is more present in solution now? That is the component B. So the temperature and the solution composition both change along the curve BC. So temperature will also change because the composition is changing along the curve BC. This is how this curve is traced. Now, for this, at temperature T1, as I mentioned, at temperature T1, solid A is in equilibrium with solution of composition X, obviously. At temperature T2, the solid A is in equilibrium with solution of composition. At temperature T1, this solid A is in equilibrium with solution of composition X. This X is corresponding to T1. Similarly, at temperature T2, with respect to further cooling, the solution of composition Y is in equilibrium with solid A now. This is T2 and corresponding composition is Y. This area ACD. In this area ACD, hence, solid A is in equilibrium with solution of varying composition. Solution of A and B I mention again. Solid A, because at this only A has started separating out, our B component has not yet started separating out. So in the area ACD, we have solid A in equilibrium with solution of varying composition. Why varying composition? Because separation of A is still continuing and the corresponding composition is being changed, and it is given by the curve AC depending upon the temperature. At eutectic point D, at eutectic temperature point D, the second solid B also begins to crystallize. When you further go on cooling, there is a point where B also starts separating out as a solid, and that point is known as eutectic point. And at that point there will be three phases now, because every solid forms a different phase. On further cooling the system, and if you further cool the system, A and B, they separate out together in a fixed ratio. In a fixed ratio, that is a fixed composition. That is, the composition of the solution remains constant, and that is represented by the point C. Here the temperature is now constant. So this is eutectic temperature corresponding to eutectic composition. Now, once we have well understood that what is the relevance of ABD and how do actually the freezing point falls when B is being added to A. Now we can very well tell that as increasing quantities of B are added to A, freezing point of A falls along the curve AC. Similarly, as increasing, if I started the explanation of this curve with respect to point A, but if I consider it with respect to B, that B is the melting point of pure B, and as I start adding A to it, all similar processes will take place and the curve BC will be traced and the freezing point of B will fall along the curve BC. Now, once we have well understood, similarly as I discussed with you about the area ACD, similarly we will discuss, we can interpret for the area BCD. As at this point solid A started separating out, similarly for this point at B prime, solid B will start separating out, and what will we have in solution behind? A and B both. Now, if at this point in this area BCD, if I say that solid B will start separating out, that means my solution of what? Both components A and B will get richer in the component A now. So in the area BCD, you will have solid B and solution of A and B. So we are now in position to define that along curve AC, we have solid A in equilibrium with solution of component B in A. So when you in examination represent the eutectic system in detail, you should be very clear about that along the curve AC, the solution of component B in A, it's not A in B, it's B in A. Along the curve AC, freezing point curve of component A. Curve BC, solid B is in equilibrium with solution of component A in B. Curve BC, freezing point curve of component B. So we can say that number of phases along AC and BC is 2. So now you don't have to cram that how the number of phases along AC and BC are 2. You very well know that you have solid A in equilibrium with the solution, that is solid A and solution. Solution forms one phase since both the components are miscible, and hence the 2 phases. So if you apply reduced phase rule now, applying the reduced phase rule, what do you get? The degrees of freedom come out to be 1, that is the system is monovariant. The composition varies with temperature along AC and BC, as I already explained you, taking the examples corresponding of T1 corresponding composition X, then T2 corresponding composition Y. The two curves, that is AC and BC, the two curves, they intersect at point C. Both the solids are in equilibrium with the solution, and the liquid, that is the liquid solution of the two components which are miscible. At C, the number of phases is 3 now, that is F prime is equal to 0. Remember, this is F prime is equal to 0. Prime indicates the reduced phase rule, that is degrees of freedom. Hence, system at C has no degree of freedom. It is an invariant point. So what do we conclude now? That under a given pressure, why do I say under a given pressure? Because we are considering this pressure to be constant now. The system consisting of two solids and their solution, two solids, that is A and B, and their solution ABL for the representation, can exist AB, two solids, and liquid, their solution, can exist only at a definite temperature and composition, and that is a definite point, as I mentioned, invariant point. This point C is the lowest temperature at which liquid solution can exist in equilibrium with the solids. Beyond this, the lowering of temperature is not possible. So this mixture of A and B of composition corresponding to point C has the lowest melting point, and this is known as eutectic point. In the area above the line AC and BC, the two components are present as homogeneous liquid solution, that is one phase, because as I discussed in the initial stages, that if I take a composition X and suppose if I take it as X prime and heat it well above the melting point of both the liquids, we'll have liquid melt. So in order to define any point in this area that is well above the melting point of these two individual components, it is necessary to specify both temperature and composition. The system is bivariant here. So after complete solidification of the solution phase, system consists of mixture of solid A and B. This is monovariant. Cooling results in just fall of temperature. There is no change in the composition. So below the line DD prime, only two solids exist. So this was the simple eutectic system diagram as applied to any two components A and B. This is applicable, this simple system is applicable for any two components that can result into eutectic mixtures, and in the upcoming video we'll be taking up lead silver system in detail as an application of simple eutectic system. Thank you.